So even though you've only covered half the subject, you can already do plenty of things with it. In integration, we'll cover lots of other applications. The central one being computation of area. And so that's what I would like to focus on today. And just make one simple point. We're going to talk about the fundamental theorem of calculus. And it's really the theorem that ties the two halves of the subject together. And that's what I'm going to show you. And it has to do with the calculation of area. And at first, I think it's totally counterintuitive, or maybe the word I should use is totally unexpected, that calculation of areas would have anything to do with opposite of differentiation. That calculating areas is in some ways inverse of taking derivatives of functions, right? Those two concepts seem to be completely unrelated. But in fact, from a certain point of view, not only are they related, they're actually the exact opposites of each other. And it's just a small example from the whole world of calculus where nature exposes itself to us in terms of rates. So in contrast to the way you've approached calculus so far, where the function is given and you have to calculate its rate of change, in other words, calculate its derivative, the way physical laws work is sort of in reverse. The nature or the law gives us the rate of change of a certain function, and from that we have to back out the function. So let's connect areas to the rate of change. And the point that I would like to underscore is that the connection is completely obvious. Newton did not invent the fundamental theorem of calculus. The fundamental theorem of calculus is basically a given. It was abundantly clear to everybody involved that this connection exists. So we're going to look at the graph of a function. So let me draw Cartesian coordinates, a familiar setup for calculus. And here's some function. And we're going to consider the area under the function, the area under this curve. So when you do this, you want to choose an arbitrary left end, and it's sometimes convenient to choose the 0 point. And then we'll choose an arbitrary value along the x-axis, and we'll actually call it x. And we have to be a little bit careful about not using the letter x too much to mean different things. So x will denote this very special point. We're interested in this area. Is it an increasing function of x or a decreasing function of x? As x increases, does this area increase or decrease? Increases, correct. Because if I move x to the right a little bit, well, it'll annex more of this area under the curve. Okay, let's give this function a name. Like, well, I'll call it a of x. That makes sense. So it's a function of variable x. So this area under the graph from 0 to x is denoted by a of x. The function itself is f of x. The function itself is f of x. And we already know something about a of x. Like you said, it's monotonically increasing for this function. For this function, it's increasing. So we want to calculate its rate of change. That's a very interesting question. That's the calculus question. Whenever you have a function, you want to calculate its rate of change. And this is an arbitrary function. Let's do it for one specific function right here. So before we answer this question, we'll do it for a much simpler function. We'll do it for a constant function first. And then try to draw broader conclusions from this one simple example. You should always do this. That's one of the ultimate mathematical skills, is to find the simplest problem that will give you an insight into what you're trying to analyze. Yes. Let me ask you another question just to get a feel for a of x. What is a of 0? 0. Because when x is at 0, there's no width to this shape, and so there is no area. Correct. So it starts at 0 and then grows. Let me ask you another question while we're at it. Do you think a of x grows faster right in the middle or right at the edge? This question could also be asked when you're painting a fence. And the fence has this nice shape, so its height varies. It's one of these fences. And you're asking yourself, what will require more paint? An incremental step in the middle here, like getting an extra foot of the fence when you're here, or getting an extra foot of the fence when you're here. What would take more paint? Yes, the fence is higher. Are you guys with me on that? We're kind of jumping a little bit ahead of ourselves, but that's great. The fence is higher. Is that all that matters? Or does it also matter that this is steeper? So what are the things that matter? How high it is? How steep it is? Or maybe both? Or maybe how curved it is? What are the things that matter for for the rate at which the area grows? Do we all agree that height matters? That if this was a super tall fence, then the next 6 inches could take a lot of paint, whereas the next 6 inches right in the middle where it was lower would not take as much? Yeah, so height definitely matters. Does the slope matter? Does the curvature matter? Well, let's see. An informal poll, no wrong answers. Who thinks the slope matters? Okay, very good. Who thinks the curvature matters? Okay, very good. Who thinks something else that we haven't considered matters? Okay. Did I already ask who thinks that only height matters? Who thinks that only height matters? Okay, no one. Interesting. Okay, well, that means that it's a very interesting question, so let's try and answer it. And when you identify the question, which is interesting, the way to answer it is to consider the simplest function that might give you an insight into the question. And the simplest function here would be the constant function. So once again, here's my graph. I will choose constant that equals to 5. So here's my 5. For a constant function, here's my f of x. F of x equals 5. And whenever the function is a constant, I suggest to you to write the triple sign equals 5. Because when you write the double sign equals 5, then to me it begins to look like an equation that you need to solve for x, and not an identical expression. So what this is saying is that f of x equals 5 at all x. So I prefer writing this triple equal sign. Okay, so for this function, we can calculate a of x exactly, right? Just think about this. If this point is x right here, that's a pretty good drawing. Let me go straight up. Okay, that's pretty good. Here is our area, a of x. And the nice thing here is that you can calculate a of x exactly. Because it's such a simple function, you can just tell me what a of x is. You can just tell me what the area under this graph is. And what is it? 5x, because it's a rectangle. That's 5 units high and x units wide. So 5x. We can take the derivative of this function right here. And the derivative of this function is 5. Good. 5. Very interesting. Actually equals the value of the function, right? That's consistent with what everybody thought. Everybody agreed that this rate of change would depend on how high this value is. And in this case, it's exactly that value. And if instead of 5 I chose 50, and this was 50 times higher, then obviously the 50 and this function was 10 times higher, then obviously, you guys agree with me that it's obvious? The area will grow 10 times as fast. It would grow at the rate of 50, not at the rate of 5. Everybody was right. It does depend on how high it is. Just the analogy with the fence answers that question. Now, most of you thought, reasonably so, that it also depends on the inclination. So let's find the simplest function that will reveal to us whether or not you're right. And I think in that case, we need to take a linear function, not just a constant, but something with a non-zero slope. And we'll see how that slope enters into the equation, okay? Okay, so let's see. I'll just go right here. Let's consider a linear function. And just to simplify the arithmetic a little bit, I'll make that function go through the origin. Fewer parameters. So the second function that we'll consider will be, let's say ax, so that we're not... Sometimes it's more convenient to use a letter. In that case, when you use a letter instead of a specific number, then when you get to the final answer, it's easier to interpret. Because when a appears in the final answer, we'll know what it means. It's the slope. So let's see. So this function is f of x. Here's our area. Okay. It's a triangle. You guys with me on that? You know how to calculate the area of a triangle? X. So this point is x. Sorry about that. The exact same construction as we did here. Choose a point x. Try to figure out what this area is. It's a triangle. What is its width? X. What is its height? Ax. What's the area of a triangle? That's right. 1/2 width times height, base times height over 2. And what is that expression? Can you evaluate it and simplify it in your head? 1/2 ax squared. Agreed. 1/2 ax squared. Great. We chose another problem where we can answer the question we posed for ourselves explicitly. Okay? Let's see how good you are at taking derivatives. What is a prime of x? Ax. You guys agree with me? Ax. The derivative is ax. Here's a puzzling thing. It's just the value of the function itself, not its slope, right? This actually equals f of x, right? Look right here. It equals f of x. It's the value of the function itself. So this example suggests to us that maybe it's just the height of the function. Maybe it's not its slope or anything else. Maybe the only thing that matters when you're painting a bridge, when you're painting a fence, is how high it is at the point where you're painting it. Maybe that alone is what allows you to calculate how much more paint you'll need. Maybe it's not the slope. And it turns out to be exactly the case, that it's not the slope. It's just the height. And let me explain to you on this graph why it's just the height. Because when you ask the questions of rate, there is really two ways of approaching it. One is the way we did it. And whenever you can do it, whenever there's some doubt, this is the approach you should pursue, where you express something as explicitly as possible, and then because you're asking the question of rate, you just take the derivative, because we've agreed for a couple hundred years now that that's what the rate of change is. It's the derivative. So in both cases, we constructed an explicit expression and just took the derivative, and there was no infinitesimals, no limits, just the process of taking the derivative. But occasionally, when you're just trying to intuit the answer, it's actually very helpful to consider the so-called infinitesimal change in x and just use a geometric argument that takes advantage of that delta x being very small. And so what you do, you consider the value of the function at x, you consider the value of the function delta x to the right, you subtract one from the other, that gives you the change in the function, and you divide it by delta x to get the rate. Does that ring a bell? You find the change in the function for a small change in the variable, and then divide by that small change in the variable as an estimate for the rate. Or if you're brave enough to take the limit, as the actual rate. So let's do the same thing here, and just use, first I'll take this small delta x, but in a moment I'll take an even smaller delta x. So here's delta x, it grabs this much more area. Okay, so it's now this much more area. So what I have on the board covered right now in green is A at x plus delta x. Right? Because this point right here is x plus delta x. And now I'm looking at area from 0 to x plus delta x. So it's area at x plus delta x. I will subtract the area between 0 and x. So in other words, I will subtract a of x. Okay? Let's find the geometric interpretation of this difference. That won't be hard, because think about this. This quantity right here is the area from 0 to x plus delta x. That's this whole area. This value right here is the area from a to x. This one right here. What happens when I subtract the latter from the former? What am I left with? Is this area right here. Let's try and think about what it might equal. In a moment it will become more clear when I make delta x even smaller and then zoom in. And I know that you guys are really good at zooming in because you zoom in on the computer all the time, right? But this will be a very special kind of zooming. It'll be zooming only in the x direction. So if any one of you ever did video editing, it's like zooming in on like a fraction of a second. Okay, so good. And then just a moment later, we'll be dividing it by delta x. Okay, now let's see, what do you think this area is? Well, you're looking at it and you're saying, I'm seeing a trapezoid. Right? So it depends on the value of the function here, and it depends on the value of the function here. And if you remember the formula for the area of a trapezoid, you have to add the two together and divide it by 2. You have to basically find their average and then multiply that by the width. But what I'm saying is that in the world of calculus, and this is the magic of calculus, you're not looking at a trapezoid. You're looking at a rectangle. And let me explain why. Because we're looking for an instantaneous rate. That's the magic of calculus. I'll say more about what I consider to be the magic of calculus in the last minute of this lecture. But basically, we don't want delta x to be this big. We want it to be smaller and smaller and smaller and smaller because we're after the instantaneous change. So we want our delta x to be like this, or even smaller, or even smaller. Now imagine that we take delta x about this small, and that you just did it on the computer, and you want to see what the hell is going on, so you zoom in on this. When you zoom in only in the x direction, right? We're not zooming in the y direction, which we did when we were studying derivatives. But right now we're doing something a little bit different, so we're only zooming in on the x. So imagine, tell me what happens, use your powers of visualization or imagination. What happens to a graph of any function if you keep zooming in on the x-axis? Does it straighten out, or is it more than straighten out? It actually flattens out. Would you agree with me that it actually flattens out? Because think about what happens. If you take the small delta x here, the corresponding value of f will be here, right? And when you zoom in and make this as wide as the original one, right? This graph will still span the same distance in y, so it'll just go like this. And then if you take an even smaller delta x, it'll be even flatter. And it'll be flatter and flatter and flatter. And at that point, if you calculate this very small annexation of area, at this point it'll be just a skin, it will definitely be this height times delta x. You guys agree with me? That's the intuition. That's why I'm saying it was always obvious to everyone 100 years before Newton. In 100 years before Newton, there may not have been Cartesian coordinates. So that's why Descartes' invention of Cartesian coordinates and the fact that people started considering graphs is so critical to the invention of calculus. This discussion could not really be had before coordinates were invented. But as soon as coordinates were invented and people started thinking about graphs of functions, this became an absolutely obvious point. They just imagined what would happen if you zoomed in on a tiny delta x. And they said, well, at that point, the function, this is the zoomed in version, will just be flat. And this additional area will basically be the value of f of x, because that's the height, times delta x, because that's the width. And when you divide it by delta x, equals just f of x. So all that matters is the height. The slope doesn't matter, the curvature doesn't matter, nothing else matters. The only thing matters is the height. And if you think back to the fence example, it really makes sense, because all you'll really be worried about at that point is just how high the fence is. If you go to the paint store, the guy there will ask you, well, how high is your, you ask, how many gallons do I need? He'll ask, how high is your fence? He won't ask you what is its curvature or what is its slope, but that's only if you're talking about infinitesimal changes. All that matters is the height. So that's this obvious, abundantly obvious insight is called the fundamental theorem of calculus. It doesn't deserve, actually, I wouldn't even give it a name. It's one of those things that are just the very basis of the subject. The subject wouldn't go anywhere if this wasn't the starting point. This is not a theorem. This is a starting point. It only became a theorem 200 years after calculus was invented, and people were pursuing totally different goals. So here's how it's written mathematically. The area under the curve is denoted by this beautiful symbol introduced by Leibniz. And the fact that we're going from 0 to x, you put a 0 here and an x here. And then what you put inside is the function you're differentiating. And I cannot use x anymore because x now means this, the right bound. So I have to I just have to write a different letter. So I will write f of t. And then for historical reasons, and historical reasons only, we're writing this funny symbol dt, which means nothing. On the one hand, it means nothing. On the other hand, as we develop our integration technique, we'll actually take fantastic advantage of this notation. So this complicated symbol denotes the area under the curve. And what we just established is an obvious fact, not a theorem. Obvious fact. So fundamental it's obvious. That if we take the derivative of this with respect to x, that the value will be precisely the value of the function at the point x. So when it's written down like this, I actually think it's quite confusing looking. So you have to get back to what it really means. And all it's really changing is that the rate at which area is growing is equal. The rate at which the area is growing basically equals the height of the function and nothing else. And you don't say the height of the function, you say the value of the function because that's the height. So the rate at which the area is changing as the right boundary moves to the right equals the height of the function. an abundantly clear fact. And this connects areas and derivatives. And that's the profound importance of this insight. Yes. So why didn't I take a bigger delta x? So calculus is focused on instantaneous rates of change. And the magic of it is that instantaneous rate of change, the rate of change over almost no time at all, is enough to reconstruct the function. You wouldn't think so at first, because you would think that if I want to calculate the area of something like this, I would want to break it up into 10 chunks and then add up together the 10 chunks. And for that, I would use a finite delta x, and maybe I would use, now we're halfway talking about approximations versus what's called Riemann sums versus, limiting process and so forth. But the magic of calculus is that you can go to the very end of that argument and beyond. So calculus makes this beautiful hop to the infinite, or to the infinitesimally small. And it just so happens that once you make that leap, you're still able to reconstruct the whole function that it came from. That's number one. And number two, when you leap to that beautiful island of calculus, and it is a leap because it involves infinities. Infinities are profoundly confusing if you don't approach them right. Infinity is a complicated concept, doesn't need to be. Again, if I were teaching calculus, I would deal with infinities in a very different way, where they don't appear as this mysterious sort of concept. Infinities are really just a wonderful idea to make a wonderful way to make logical arguments. But the fact remains that calculus deals with this utmost, taking this idea of a small change to utmost limit. So much so that you make this leap to the beautiful island of calculus, where everything is simple and elegant compared to this everyday world where finite changes are difficult to calculate and expressions become very complicated and things are basically impossible. But when you take that leap to the infinitesimal small quantities, that beautiful calculus limit, everything becomes simple. And the world is reduced to f equals ma, and it's reduced to taking derivatives, and what we've just justified, doing the opposite, going from the derivative back to the function that it's the derivative of. It's called anti-differentiation or integration. Those are two synonyms. Integration is basically anti-differentiation. And this right here is a justification for it, because the rate of change in area is something that we know. If we did this analysis and got some complicated expression here, not just f of x, that wouldn't be helpful. But as you can see, what I said at the beginning of the lecture is true. Nature and mathematics has this tendency to present problems to us in the form the derivative of something is known. Figure out that something. And that's what we see right here. We don't know what area is. It's a complicated thing. But the calculus leap has allowed us to find the area of any shape whatsoever, just about, one way or another. And that's because this simple insight, this obvious insight, shows us that the derivative of area is the function itself. In other words, the derivative is known. So it's an invitation to calculate antiderivatives. And that's what we're going to do for at least the next 4 weeks. All we're going to do starting next week is calculate antiderivatives. And this will be, for the time being, the only point, the only insight that justifies that activity at all. But take my word for it. So many things in the world are presented to us by greater powers in the form derivative equals something that you know. So go ahead and back out the original function. Take the antiderivative.